and Chloe right behind. Do you guys jump in? You guys have the same classes? Do you go? You and Chloe have the same class at all besides science? Hi, Kylie. All right, like your last class, did you guys both get out at the same time? Everything. Oh my gosh, how's that possible? Because it looks like you guys got out of one class and jumped into another class. Oh my gosh. That is so amazing. So wait a minute, because you guys are both MCs, right? You guys are both MCs. That's what it is. Your names are close. Yes, that's what it is. They're all alphabetical. So you guys are in the MC group. Nice. You guys got a gang, MC gang. Nice, nice. I didn't I realize that. When I start looking for my advisory, mine goes from C to E. So that's who I have. I got the C to E people. So nice. All right, guys, let's do a poll real quick here. Let's do a poll. Would you rather? Would you rather? And let's do A and B on this one and see if we got anything here. Start a poll. Would you rather have the love of your life, but be broke, be forever alone, be rich? So it depends. That'll tell me a lot about you guys. Okay. What do you think, Kylie, Gabby? What do you think? Love of your life, be broke, be forever alone, be rich. All right, so let's see what they say here. Oh, you guys are all A people. You guys are so romantic. Oh my gosh, 50-50. Oh my gosh, how's that possible? Publish a poll. Let's do this next one. All right, start a poll. This is poll number 2. Would you have your back cracked by a chiropractor, have your mind explored by a psychic to uncover the deepest thoughts? Oh, I would love the psychic. Wouldn't you guys like the psychic? Or you guys all, oh, you know what it is. You guys are all been sitting way too long in these seats. Right? You guys have been sitting in these seats way too long. I want a psychic to tell me. Let me see what they think. Oh my gosh, it was almost 50-50 again. Wow, how is that possible? All right, start a poll. We'll do number 3. I'm not going to get many people here today, it looks like. 3. All right. Never do laundry, never do the dishes. Okay. All right. Never do laundry, never do the dishes. You know, there is an electronic device that will do your laundry for you, but you still have to sort them. And once you sort them, it'll you just pick what you want to wear and it'll send it to you. It's probably too expensive. I think it needs to be able to wash and fold first. You know what I mean? Never do dishes. You guys, yeah, you guys are on that one for sure. All right. Well, thank you guys for coming in. It is a Monday. Hopefully, you had a nice weekend. It's supposed to rain all day today. Tomorrow, I think it's supposed to rain all day. It's supposed to rain today. But anybody see the aurora borealis at all? Anybody see that? I was just too cloudy where I was. Just too cloudy. You saw it? Sadly, no. Okay. All right. So cool. Oh my gosh, Kylie saw it. Oh, all right. Yeah, it's been so cloudy. Yeah, they had the solar storms this weekend and the cloudiness. Didn't know it was happening. Okay. Check outside in the middle. How late were you out, Kylie? How late did you go? When did you see it? Back to back? Wow. So what time did you go out to see? Did you have to get up really late or did it come about 10:30? Okay. All right. Check I'll check for you guys, but I think that there might be some residuals, but yeah, I mean it's blows your mind. Didn't it, Kylie? Just kind of like, wow, this is the coolest thing besides a solar eclipse. Yeah. Yep. Hey, so what we're going to do today, guys, we're going to be talking about static electricity. So let me show you a couple things that are kind of cool. All right, let me go show you this. You gotta go back on this one. Tried this with a balloon, salt and pepper. Take your balloon and look at that. Woo, that is so cool. So we're talking about static electricity, and we got a lot of different things to do today. One of them is John Travolta. How many people have done this and got somebody shocked? Rub your foot, and then you touch the doorknob. Oh, thanks, Kylie. I would love that. No way. That is so cool. Can you send me that, Chloe? I'd love to see if there's anything. I have quite a few times. Okay. I get mad after. What? Okay. Oh yeah, you get shocked. Yeah. I pet my cat and it's I'm getting shocked. This is kind of cool. Where is this one? Static electricity. Okay. So this is kind of something we do in if you were in a science class and they had a good science laboratory. These things are expensive. This is a Van de Graaff generator. Anybody ever had a Van de Graaff generator? It's a big ball, and you touch it and your hair stands on end. Anybody do that? Go into a science show where they do that. It's really cool. Let me show you this. So this is Steve Spangler.
Machine. It's called a Van de Graaff generator.
You guys hear him okay?
You and I have never done this before, and this is a brand new one. I've never even tried this one out on 9 News before, so this is great. This is how we teach kids about electrons and really an electron elevator and how it sends the electrons over the top here. So here's what happens. There's a crank that's here.
Right.
The crank's going to turn the motor on the bottom, and when I turn it like this, you're going to actually start to feel some of the. Oh, do you feel that? There's a little electricity that's in the air.
Is that weird?
All right, so here's what I'm going to do. You hang on to the ball, okay? And I'm going to hold on to this little grounding thing over here. And Vinny's going to dim the lights a little bit, and I'm going to twist it. And watch what happens here. You're going to get a nice little, get a little closer. Oh, there you go. Isn't that a great one?
That's really cool.
Hey, Leah, good to see you. Carmen.
For every inch of spark, it's about 50,000 volts. So that was a really good one. Now here, this is more fun. You hang onto this.
Oh, okay.
So hang onto this. Now you can feel it. Ready? So get a little closer. See how that?
Yeah.
All right. So the lights come up because here's what we're gonna do. This cranking thing is for sissies. So we're gonna move it to the motor. All right. So here we go.
Steve, now wait a second. You said before that we were not going to do the motor.
I know, but now he's lying. So here's what we're going to do now. So now I'm going to hang onto this. And now when we flip on the motor here, now you really can kind of build up those electrons. And that's what we're doing. This little electron elevator is sending the electrons to the top there, and it's jumping. So we get all this negative charge. And you feel it around your body, don't you? Is that crazy?
Did you say to me earlier that this is what you feel like just before you die on pipe speed?
Oh, no, it's this part. All right, so here's what I want you to do. So now you put your hand on the ball.
What?
Right? So it's okay to put this hand on the ball like that. No, just one. Which hand do you use the least?
The left.
Okay, so you're there. Then you're good. So now we flip it on, and so now you're going to start to feel the electricity around your body. You start to feel it around?
Yeah, a little bit. Do you want me to shake my hair out?
No.
Oh.
You see that? Yes. See, there's a little spark in there. See that kind of fun? Yes. So there's a little bit of sparking, but it's okay. So now here we can build up some of the electrons this way. So if you go this way, these are just little pipe hands. So if you start to see the repelling charges, you can kind of see what happens here. So it starts lifting up the that kind of fun. Cool. So there is this piece too. We have to tell people in Colorado that when the lightning hits, you count to 5, right? So when you see the flash of lightning, 1,001, 1,002, for every 5 seconds, it's a mile away.
Okay.
They consider a real danger zone in Colorado between a mile and 2 miles. So believe it or not, you can count to 10.
Anybody ever count
hear the thunder
between the lightning and the
that's
thunder?
That's pretty dangerous. So you got to get out of there.
Absolutely.
Get out of there. Hey, here's our special guest, Barbie. So hang on to Barbie. All right. So now you put your hand here.
Yes.
And now I'm going to crank this up, and you should be. There's a little of electricity in the air. Do you feel? Oh, see, see when you touch. Is that funny? There's just a little electricity.
All right. So a good thing to talk about as far as this idea that lightning strikes. Okay, so that's why they close pools and outdoor events. Get down on the ground, right? Don't stand up. Many times, I mean, there's several cases where people are playing baseball and then the pitcher gets hit by lightning and then it hits everybody in the infield and the pitcher gets killed. So you got to be really careful of that. So we're talking about electric force today. Electric force is an invisible force created by electrically charged particles. So this week, what we're going to be doing is we're going to be talking about some really cool things, series circuits, parallel circuits. By the end of this, you will know which kind of Christmas light to buy so that when you burn one out, everything doesn't go out. Okay. I mean, back in my day, we didn't have that. And every Christmas light depended on one bulb going out, and we had to find that in the string. That was terrible. How many people have had to do that where they plug in the Christmas lights, none of them working, and you got to find the light bulb? Anybody have to do that? Find the light bulb? Because there are like find the light bulb kind of things. Oh yeah, your dad would probably have to do that. It's his job to get the Christmas lights, right? Oh yeah, I don't know about the picture, but yeah. Yeah, and what's really weird is like their clothes get taken off, like most of their clothes are gone. So it doesn't like, yeah. Yeah, it always happens with Halloween lights, right? Yep, yep. So when you buy some, you'll tell your parents, don't buy those, buy these. And that special kind, whether it's a series circuit or a parallel circuit, and they're a little bit more expensive. So, but electric force. Now, what we're going to try to do today is to kind of explain electric force, but there are questions on the assignment 1 where you have to figure out the charge on something, and that really drives people crazy. I recommend that you use a calculator when you do this. Okay. All right, so I can describe the structure of an atom. So again, we're going to go back to chemistry from last year and talk about the structure. You probably forgot about it, but you'll remember. I can explain static electricity. All right, so electrical charge, the physical properties of a particle that causes it to be attracted to nearby opposite charges or repelled by nearby like charges. Electrons are negative, right? Protons are positive. Electrical force is an invisible force. We did this one already. An electrical charge so remember we have the positive charge, and then we have the negative charge in an element, right? Everything's consisted of positive and negative charges. The proton is the positive charge. The electron is the negative charge. All right, so what type of particle exerts electric force? Are they just positively charged particles? Are they negatively charged particles? Are they neutral particles, or both positive and negative? All right, we got 4 out of 5. How did we only get 4 out of 5? Oh my gosh, we only have that many people. All right, so this was poll 1. Okay, let me try that again. Poll 1. Let me try that again. I didn't publish the poll. Let's start a poll. Let's see. Okay. All right, so this is better. This is better. Positively charged or negatively charged, a neutral particle, or both. Neutral particles are neutral, so they have no charge, right? And negatively charged, we often think that negatively charged has charges. They do. But if you get 7 out of 14, wow, we got half the class. You guys are great for a Monday. I'm glad you had a good time. How about you, DeAndre? Did you get in there? Yeah, DeAndre, John, and Kylie, Rachel, Chloe, Gabby. Thank you, guys. All right, so it's both, right? To get a charge, you have to have both of them. Let me give this, circle it. Both of them are charging. And again, what you remember from these, this is a reminder that oppositely charged particles attract each other. Negatively charged particles or like charges, opposite charges attract, like charges repel. So that means the negative charges repel the negative charges, positive repel the positive charges. Okay, so what did I say? Complete this statement. It says complete particles with opposite charges do what? And particles with the same charges do what? Okay, so what do you think? A, attract each other, and B, repel each other? Or B, repel each other, attract each other? So particles with opposite charges repel and then attract, or is it opposite charges attract and then positive particles of the same charge repel? So we've got half and half of you guys are saying A, and some of you saying B. So it's A, particles with the opposite charges attract, so positive and negative attract, and the same charges, negative and negative, or positive and positive, repel. Okay, good job, guys. So electrons and protons cancel each other out, and they become a neutral. So if I do, let me draw this out here. Let's see if I can do this with my finger here. So if I do a lithium, right, as in the nucleus, has 3 positive charges. It has 2 electron clouds. Okay, I'm going to draw this. It has 2 in the first and 1 in the second. All right, so remember, lithium is a metal. It's a group 1 metal, and it has 1 electron in its outer shell. So the 3 plus and the 3 minuses cancel each other out. If I want to make this a negative charge, so this is what they call a neutral charge, then that charge is equal 0. So plus 3 minus 3, if you use your calculator, it should say 0, right? Okay. So let's take a look at beryllium, because again, it's going to be questioned on the assignment 1. So beryllium has 4 protons. So it has 2 electrons in the first shell, 2 electrons in the second shell, right? So that is plus 4 and minus 4. All right, so that one has a net charge of 0, plus, minus, okay? This one I want to make a -1, so I'm going to do 2 electrons in the first shell, 3 electrons in the second shell. So this is plus 4 minus 5, right? So plus 4 minus 5 going to give us a -1. And this one I want to make a positive charge, so I'm going to put 2 electrons here and 1 electron there. So now I've got plus 4 minus 3. Can't draw that. Minus 3 gives me a plus 1. And again, like I said, use your calculator if you have trouble with integers, right? And when you put them in, plus 4 minus, you don't have to put the plus in, but if you put 4 minus 4, you get 0. 4 minus 5, you get -1. 4 minus 3, you get a positive 1. Okay, let's move on to this. All right, so one of the things that probably is not one of those things that's very intuitive here is that an electron, depending on where it is, if it's really close to the proton, it has a lot of strength. So the particle of electric charge is stronger the closer it is to the plus charge. The strength of an electric field decreases as you move away. So this one, the A, is the closest, so it has the most charge. It has the strongest charge. B is a little further away. So as we move away, the electrically charged particle, the strength of the charge gets less. Okay, so D would have the least amount of charge. And that doesn't make sense. It seems like, oh man, I'm fighting to get away. The further I get away, I'm really strong. But in this particular case, if one is close and doesn't go any closer, then it's the strongest. And that makes sense if you think about our electron model. When we had the electron model, our valence electrons were way out there, and they were easily captured or taken away, okay, because they weren't being pulled as tightly by the protons, okay? So let's take a look here. So what did I just say? Which one had the greatest strength? Was it A because it was close, or D because it's far away? You can kind of omit B and C. Just want to let you know which one was the strongest. Was it A because it was close, or D because it was far away? All right, thanks guys for getting in there. 4 out of 14. DeAndre, Kendrick, Chloe, John, and Gabby, Kylie. So you are correct if you said A because it was close. Because it says right here, okay, and I'll show it to you again. The strength of an electric field decreases as you move away. And again, all I can tell you is that when we're looking at the valence electrons from last year, the ones that were in the outer orbits were easily taken away, okay? They had less strength. So closer means stronger. Closer, stronger, farther. Yeah, so it's an opposite kind of thing here. So magnetic fields are unidirectional. They move from positive to negative. And there's some confusion over that, but we're going to use what they call conventional electric fields. We use this is something that there's some controversy over. We'll talk about that a little bit later. So electric fields, so notice that the positive charges, the field lines go out and the negative field lines go in. So when we draw these, we draw them from plus to minus and put the arrows toward that. Notice that the bottom one has positively charged and they're repelling each other. They push out and they repel each other. They reflect each other. So if I were to draw this, I would take this line and go here, this line go there. They don't cross each other. I just put my arrows this way. Okay, so that's what we try to do. A point away from, okay, so let's ask you this question. What did I just say? Electric field lines either A, point away from the positive and toward the negative, or point toward the positive and away from the negative. Okay, so let's see what you guys remember. All right, so thanks, Dylan. Thanks, Gabby, John, Kendrick, Chloe, Grace. Thanks so much for getting in there. How about you, DeAndre? DeAndre, you got to get those dogs out about now, don't you? Isn't this the time you got to get going for the dogs? Or did they already take care of them today? Did you get them already? Because it's like the dogs have to go out. And then you got to get them back in. Yeah. I know. I remember. So this one is A. Yep. So DeAndre's got dogs, and again, we're talking about, yeah, they do, when they want to go out, they gotta go. And if it's weather, but the weather is cold, my dog is like, goes out, doesn't like to get her feet wet, so she tries to go to the bathroom as close to the edge of the sidewalk as possible, and then wants to come back right back in. It's wet. I'm not coming out. I'm not going out. So it's like 5 seconds later. All right, so we draw our electric field lines from positive to negative. They never cross. All right, and energy is contained within the electric field. The energy is called electric energy. Electricity energy is also called electricity. And electricity can build up in an object called static electricity, which we've been talking about, right? And objects with both positive and negative charges. So we can take some of those away. And we can get buildup, like we can rub the carpet and we can get shocked when we touch the doorknob. So we build up electric start to get negative charges added to us, and then we have to get rid of them. And that's how lightning works too. Lightning, a buildup of the moving charged particles in a cloud, and they start to build up negative force, negative electricity, or negative charges, and then they have to release, right? So, but it takes a lot because air is not very conductive. It's not like a wire. That's why if you want to get your house, if you're in an area where there's a lot of lightning strikes, you'll have a metal pole on the top of your house with wires that go around the house and down into the ground, so they get grounded, so you get hit on that spike and not hit on the wood frame and cause a fire. So they do that especially to water towers. They do that for buildings that are really tall. And again, one of the things that you have to be careful of is that if you can't get away from electricity, static electricity and lightning, and there's no shelter, don't go by a tree, right? That's what those get hit the most. Find a place to lie down on the ground, right? So that you're not a highest thing in the air, right? So just lying down on the ground is the best thing to do if you can't find some shelter. Not a tree, not a tree. The tree's going to get hit. Okay, so static electricity. So rubbing a balloon with a wool mitten. All right, the balloon gains electric negative charges, right? So notice that they're positive, negative, positive, negative. If I look at this, 1, 2, 3, this is neutral. So these cancel these, right? This cancels those. So it's neutral, but when I rub it with a wool mitten, the negative charges here go over. Give you an example of that. Let me show you here a second. Okay, so all right, let's go. All right, that one, not that one. Okay, here we go. Balloons and, okay, share this screen with you. Balloons and a wool sweater. Okay, so let me reset this, reset the balloon. Okay, so notice, so if I were to draw on this, this would be 0 charge. I can't draw on that. Okay, can't draw on that because so this is 0 charge. These cancel each other out, 0 charge. But if I go and notice this wool sweater is 0 charge, but if I go ahead, I'm going to add a wall here. So notice, it's not supposed to stick to the wall. Why are you sticking? All right, just because it is. So notice that up against this wool sweater, I picked up all this negative charge, and when I go over to the wall, notice that the negative charges are repelled and pushed against as far away from the wall as possible, and the positive charges are caught there. So we've got a negative and positive charge. Now, if I remove the wall, what do you think is going to happen? If I remove the wall, what do you think these negative charges are going to do? Anybody have an idea? Is it going to just stay right there when I remove the wall, or is it going to move somewhere? Go back to what? Do you think it's going to go back to the sweater? Okay. Anybody believe that? It's going to go back to the sweater? Yes, no? Back to the sweater? Yeah, Gabby says yeah. Anybody else? Or is everybody gone get some coffee? Get some coffee, bring it with you. All right. I mean, if DeAndre is letting his dogs wait for him, he's doing a great job. Thanks, DeAndre. All right, so let's see. We're going to remove the wall here. Yep, stuck to the sweater, right? Okay, so let me do this. I'm going to reset, and I'm going to put 2 balloons. Okay, so what if I get some electric charges here? What's going to happen to this balloon? What do you think? They already went out. Oh, all right, DeAndre, you did your job. So what do you think the balloon's going to do? They're going to come closer to each other, or are they going to repel each other? What do you think? Repel or attract? A repel or attract? Repel. Okay, let's take a look. Let's see. Yep, it's attracted to the wool sweater, isn't it? All right. How about, let's do this. Let's get this one over here. Now look at that. So they're both negatively charged. They don't want to be close to each other at all. So opposites attract. Okay, so what you guys are going to do, we're going to stop right here. This is kind of fun. This is a FET thing. So what I'm going to give you guys is John Travolta. John Travolta. Okay, so I'm going to give you this, right? And you're going to do the exit quiz. Okay, so I'm going to give you John, get it, Travolta. Cool, huh? He gets to shock himself here, okay? Right, and they're going to get a quizzes. Right, so play around with this one. And you are going to get a quizzes from me. Where are you? Here we go. All right, did I leave you? Oh, here it is. Got it. That's not it. We go here. Here we go. And you're going to answer these 11 questions, okay? You're going to answer these 11 questions, but you got to play with the John Travolta first, okay? So, all right. So here is the exit quiz. 5.13 exit. Oh, that's not a 5. That's a percent sign. Exit. All right. So do that. Okay. So you got John Travolta and the exit quiz. All right. Publish that. So get me a point for that. Now, what I'm going to do is I'm going to give you guys some time to play